The College Algebra Lesson 26 demo. All right, let's look at the function x squared minus 9 over x plus 3. What x values are excluded from the domain? Anything that would make the denominator 0. So x cannot be negative 3. All right, let's factor and reduce this thing to lowest terms. After we've identified what you can't plug in, factor and reduce to lowest terms. So x squared minus 9 factors to x plus 3, x minus 3 over x plus 3. I have the same factor in the numerator and the denominator, so I just get x minus 3. And that's just a line, right? F of x equals x minus 3. It's got a y-intercept of negative 3, a slope of 1. Y-intercept negative 3. Slope of 1 means it would go like here, 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 here. Connect the points, right? Except I do have to be careful to not plug in the negative 3, right? At the very beginning, I noted that x cannot be negative 3. So I want to go back to my graph and find the point where x is negative 3 right here, this point here. That actually is not a point on the graph. Okay? I have to make that a hole. Put an open circle there because x equals negative 3 is not part of the domain. So it's often hard for people to wrap their heads around, and this is how I try to explain it. So x squared minus 9 over x plus 3 is equal to x minus 3, right? These are equivalent functions, except this one you can't plug negative 3 into, and this one you can, right? So there's one small difference. These two are identical. They are equal, except this one's domain is all x's except negative 3, and this one's domain is all real numbers. So their graphs look identical, except one of them has a hole. You can't put the negative 3 in. All right, in general, to graph functions that are not transformations of 1 over x or 1 over x squared, we just follow this 8-point process. First, make sure your rational function is fully reduced and find its domain. Check for symmetry, find the y-intercept and the x-intercepts if there are any. Find vertical asymptotes, find horizontal asymptotes. Vertical asymptotes are found by setting the denominator equal to 0 and solving for x after you've reduced and canceled. Horizontal asymptotes are found by looking at the degree of the numerator and the denominator, and we'll talk more about that in a couple minutes. Then plot a few points, and then connect your points using the asymptotes and symmetry as a guide. So let's look at finding vertical asymptotes and holes. So these are places where the denominator equals 0. So we're always going to factor everything and cancel if we can. So we've got x plus 1 on the top, and then this denominator factors to x times x plus 4. Nothing cancels, so I have an asymptote at 0 and an asymptote at negative 4. No holes. Now in this one, h of x is x squared plus 5x plus 6 over x squared plus 3x plus 2. Factor everything possible. So this is x plus 3 times x plus 2. And this one is x plus 1 times x plus 2. So my domain says I can't put in a negative 1 or a negative 2 because either of those would make the denominator 0. But the fact that it also makes the numerator 0 when x is negative 2 means that at x equals negative 2, I actually have a hole. Okay. Now, when I look at my reduced version of the function, the place where the denominator equals 0 is going to be a vertical asymptote. So when x equals negative 1, we've got this vertical asymptote. So x values that make the denominator 0 can result in a vertical asymptote or a hole. You tend to get a vertical asymptote if the x value makes the denominator but not the numerator 0. You may get a hole when the x value makes both the denominator and the numerator 0. Right? So typically that happens like when you're reducing, you will notice it by saying you get a factor that cancels. That should be a tip-off that you might have a hole. Okay, thinking about end behavior for a rational function, horizontal asymptotes. So thinking about end behavior for a few rational functions, here I've got f of x equals 9x squared over 3x squared plus 1. And I want to think about what happens to the y values when the x values get really, really big. So I'm going to plug in 10, 100, 1,000, a million. If you think of these as dollars, right, like then a million squared over a million squared, that's so big that the plus 1 doesn't even really matter, right? Doesn't even really matter. And the 9 and the 3, so if you have $1 million and I have $1 million, you've got 9 million and I've got 3 million, right? So this ratio is basically 9/3, right? Because the x squareds are the same size, those would cancel. And so I put approximately equal to, because this is only true when x is really, really, really big. When x is really, 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 really big, that plus 1 doesn't mean anything. And then you can cancel, right? So this would be approximately 9x squared over 3x squared, because the plus 1 is like $1. You're talking a million squared. $1 is nothing. And then you can reduce that and you get 3. So y equals 3 is my asymptote here. And you can see it in the graph, horizontal asymptote at y equals 3. In part B, g of x is 9x over 3x squared plus 1. Again, pretend we're talking dollars. You're going to plug a million in for x. So 3 times a million squared plus 1, like that one measly dollar could easily get lost, right? It's like so small in comparison to everything else that when x is really big, this is approximately equal to 9x over 3x squared. So then you cancel and you get 3 on top, x on the bottom. And then when x is really, really, really big, 3 over x goes to 0. Right? Because we're talking about what happens when x is very, 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 very large. 3 over 10, 3 over 100, 3 over 1,000, 3 over a million is a very small number. So as x approaches infinity, f of x approaches 0. And then similar thing here, you can drop the plus 1 because x cubed and x squared, when you're plugging in really big x's, that plus 1 doesn't really make much of a difference. And then when you reduce this, you get 3x, which when x is really, really big goes to infinity. So there's no asymptote here. The end behavior is just to infinity or negative infinity. Shortcut for finding horizontal asymptotes. Look at the degrees. You want to compare the degree of the numerator and the denominator. If the numerator degree is less than the denominator degree, then y equals 0 is the horizontal asymptote. That's the x-axis. If the degree of the numerator equals the degree of the denominator, then y equals a over b is the horizontal asymptote. A is the leading coefficient of the numerator and b is the leading coefficient of the denominator. If the degree of the numerator is greater than the degree of the denominator, then there's no horizontal asymptote. Okay, so a couple things about asymptotes. A rational function can have several vertical asymptotes, but it can have at most one horizontal. And although a graph can never intersect a vertical asymptote, it may cross its horizontal asymptote. The horizontal asymptote just governs end behavior, which is the far right and far left of the graph. All right, let's graph 2x squared over x squared minus 9. I'm going to start by looking at the domain. Right, so that would be Anything that would make my denominator 0 has to be excluded. So I would say the set of all x's such that x does not equal positive or negative 3. Positive or negative 3 would both make my denominator 0. 2, factor and reduce. Okay, so I've got 2x squared over x plus 3, x minus 3. Nothing cancels. I can't reduce this at all, so I have no holes. There's no holes in the graph here. So 3 would be to find vertical asymptotes. Those happen where the denominator equals 0. Once I've factored and canceled, I set the denominator equal to 0, and I get x's plus or minus 3. Put those in right now. Vertical asymptotes. Okay, step 4, horizontal asymptotes. Compare the degree of your numerator and your denominator. So I have 2x squared over x squared minus 9. Numerator and denominator have the same degree, which means that my horizontal asymptote is the ratio of the leading coefficients, in this case 2 over 1. So y equals 2 is my horizontal asymptote. I should find x and y intercepts. So y-intercept happens when you plug 0 in for x. What's the name of this function? F, okay. F of 0, y-intercept. So that would be 0 over negative 9, which is 0. And then x-intercepts, those happen when the numerator equals 0. So I've got intercept, x and y intercept at 0, so the origin. And then I need to plot a few more points. I should plot points on either side of my asymptote and between any asymptotes and points that I already have. So 6, plot some points. So what would be some good points to plot? I should plot something to the left of this asymptote. So maybe I'll use x equals negative 5. I should plot something between the asymptote and the one point I've plotted, between negative 3 and 0. Maybe I'll do negative 1. Something between 0 and 3, I'll do positive 1. And then something after 3, I'll do 5. And I need to get a y value for each of those. So 2x squared over x squared minus 9. Might have a calculator do this for me. Okay, so I typed into y equals in my calculator. I put the function 2x squared over x squared minus 9. I went to the table, typed in the x values I wanted, and my y values are 3 and an eighth, 3.125, negative a quarter, negative a quarter, and 3.125. So if I plot those points, that should give me a pretty good picture of how to connect everything using the asymptotes as a guide. So negative 5, about 3 and an eighth is there. Negative 1 is negative a quarter. Oops. 1 is negative a quarter. And then 5 is 3 and an eighth. So like that. Okay, so I know that I've got my points plotted. I know that generally what happens with rational functions is that it approaches the asymptotes. So this is, I'm going to say, approaches the asymptotes like that. This point goes up to that asymptote and down towards that asymptote. And then over here, these come down and approach the vertical asymptotes. All right, one more together, and then we'll do the activities. Okay, 4x over x squared minus 1. So 1, look at the domain. Anything that would make my denominator 0, so that would be plus or minus 1. The set of all x's such that x does not equal plus or minus 1. 2, factor and cancel anything. So I have 4x over x plus 1, x minus 1. Nothing cancels, so that tells me I have no holes, right? 3, vertical asymptotes. Those happen when the denominator is 0, so that would happen at x equals plus or minus 1. 4, horizontal asymptotes. Compare the degree of the numerator and the degree of the denominator. So I've got 4x over x squared minus 1. If we're talking x is $1 million, the minus $1 doesn't make much of a difference. So you have 4x over x squared. X's cancel, and you get 4 over x, which goes to 0 when x is really big. Heads towards 0. So I can plot my asymptotes now. I have 1 and negative 1. And horizontal asymptote at 0. X and Y intercepts. So y-intercept happens when you plug 0 in. So f of 0, that would be 0 over negative 1, which is 0. X-intercepts happen when the numerator is 0. That happens at 0. So I have 0, 0 is a point on my graph. And then plot some points. I need something to the left of my leftmost vertical asymptote, something between my asymptote and the point I have, and then the point and the asymptote, and then to the right of the asymptote. So let's see, I want to say x, y. Maybe negative 2, something to the left of my first asymptote. So something over here like negative 2. Something between this asymptote and this point, so that would be like negative 1/2. Something between this point and this asymptote, positive 1/2. And then 2. So do negative 1/2, positive 1/2, and 2. Once I have those points, that should be enough to sketch a rough version of the graph. So I'm having my calculator get these. Go to y equals, I'm going to type in my function, which is 4x over x squared minus 1, and I should have put parentheses around that denominator. Go to my table, and I'm going to type in the x values I want. Negative 2, negative 0.5, 0.5, and 2. So we get negative 2 2/3. We'll just round to negative 2.7. 2.7. Negative 2.7 and 2.7. All right, so I'm going to plot those points. Negative 2, negative 2.7, negative 1/2, positive 2.7, positive 1/2, negative 2.7, and 2, positive 2.7. Then use my asymptotes as a guide. So each region of my graph has some points, and then I can just draw approaching the asymptotes. So this goes like this goes down towards this asymptote, in between these two asymptotes, it looks like that, must go up towards the asymptote on the left, and this heads down towards the asymptote on the right. And then this point right here is guided by the two asymptotes, like that.